I have some bad news. Reality is rarely accurately modeled as a single simple process. Instead, what you often encounter in thermodynamics are sets of processes that are connected together at the endpoints. Let's consider this problem, which has three processes that are distinct from one another. The first one, process 1 to 2, is a polytropic process. The second one, process 2 to 3, is operating at fixed volume, and the third one, process 3 to 4, is operating at fixed pressure. So three physically distinct processes that are linked together at the endpoints. But the problem is we don't actually know all of the endpoints, so we can't even compute the total work until we at least figure out what the pressures and volumes are in between the various processes. The very first thing I would do in trying to solve a problem like this is just make it absolutely clear what we know and what we don't yet know. Well, we certainly know the initial state. And when I say state, I really just mean the pressure and volume values. So P1 and V1 we know, and we know that they're going to be connected to P2 and V2 via a polytropic process with n equals 2. Now, if you look at process 1 to 2, we know V2. It's 3.8 meters cubed. But we don't know P2, so we're going to put question marks by that. We'll have to compute that shortly. We also know that that state, P2 and V2, is connected via constant volume process to the third state. Well, it's constant volume, so we know V3. V3 has to be equal to V2. We don't yet know the value of P3, but from the description of process 2 to 3, the pressure is reduced to half its previous value, we do know that P3 is 1/2 P2. So if we can figure out P2, we'll get P3 quickly. For the final step, we have a constant pressure process that gets us to state 4. And since it's constant pressure, we actually do know that P4 must be equal to P3, right? They're both related in the same way to P2. Now, what about V4? Well, we're told that the volume is decreased to its initial value, which was V1. V1 was 1 cubic meter, V4 has to be 1 cubic meter. Now we have the CliffsNotes version of this problem, relatively simplified compared to all that text. The next thing we should do is draw a PV diagram. There's two reasons to do this. One is the problem asks us to. The second is that if we draw out a PV diagram, that'll help us catch things like sign errors later on when we do our calculations. So let's put down a general set of axes, and then let's put down the first data point without putting tick marks on our axes. It doesn't really matter where we put the first one. Simultaneously, I'm going to have a little diagram of a piston down here, because as we go from, for instance, state 1 to state 2, we want to keep in mind what a piston would do. That'll help us evaluate what should be going on with the work. So, going from state 1 to state 2, which way should we go? Well, clearly the volume increases, so we should go to the right on this plot. Should the pressure increase or decrease? We know that without doing any calculations. PV to the n is a constant for a polytropic process. If V increases, P has to decrease. There was a reason I put 0.1 way up there in the upper left. 0.2 is going to be down on the lower right. And as that happens, the piston has to expand, right? Because the gas cylinder has gotten larger, it now occupies a larger volume. Good link between the physical process and the thing that we're drawing on the PV diagram. What about the next step? Well, this one should be fairly easy to draw. It's a constant volume process. On a PV diagram, a constant volume process should be a vertical line. We also know that the pressure drops to 1/2 its value, so if you assume that the bottom of the graph actually is P equals 0, then we expect a vertical line that goes straight down to 0.3. Now you may notice that the piston didn't move during that process. It's not because I got lazy with the animation, it's a constant volume process. The piston doesn't move. Okay, that's weird. How did we decrease pressure without changing the volume? You'll have to think about that a little bit. One thing we're not accounting for in any of these calculations is heat transfer, so we really don't know what's going on with the total system energy. We're just worried about what's going on with the work for now. The last process, going from 3 to 4. It's a constant pressure process, so on a PV diagram that will be a horizontal line, and we know that we have to end up at the same volume that we started with, so that's fairly easy to draw. Now if that happens, that also means that the piston simultaneously must compress. And we get back to the volume at which we started, but the pressure is severely diminished from its initial value. Okay, our goal is to compute P2, P3, and P4, and the works associated with process 1 to 2, 2 to 3, and 3 to 4. Let's jump in, we're just going to do this in order. So the first step is a polytropic process getting from state 1 to state 2. We can use PV to the n equals constant. That means that P1 V1 to the n equals P2 V2 to the n. We can solve for P2 in a pretty straightforward fashion. We know the values and the value of N, put those in, and we get out that P2 is 55.4 kilopascals. I'm going to replace those question marks up near the top with this value so that we don't forget it. Alright, so we have that, and we'll move things up. Now let's compute the work involved in process 1 to 2. The work is the integral of P dV, and we know for a polytropic process that P is a function of V. If you've practiced this before, this may look familiar. P is a constant divided by V squared in this particular case since N was equal to 2, so we can put that expression into our work integral. We can pull out the P1 V1 squared, that's just a constant. That gives us an integral of dV over V squared, which we'll evaluate according to the appropriate limits of integration. So we do that, we plug in the relevant values, and sure enough we get that the work in going from state 1 to state 2 is a positive 589 kilojoules. I'm going to write the work values over here on the PV plot so that later on we can add them and understand what parts of the curve they're associated with. Okay, we've solved two things. Next step, figuring out P3. Oh, I like this calculation. P3 is 1/2 of P2. You put in the values, you get out that P3 is 27.7 kilopascals. Relatively straightforward. We'll write that at the top. What about the work in going from state 2 to state 3? Well, it's still true that it's the integral of P dV. Something's weird here. So V2 and V3 are the same, right? They're both 3.8 meters cubed. It was a constant volume process after all. So if you're taking the integral and the limits of integration are identical, it's 0, right? You could also get this another way. If you look over here at the PV plot, that's a vertical line. You may remember from your lecture notes that the magnitude of the work is the area under a curve for a particular process. The area under a vertical line is also 0. So the work in going from state 2 to state 3, well, it's just 0. Okay. Makes sense. The piston didn't move, remember, so that's not too big of a surprise. Work 2, 3 is 0. We'll put it over on our PV plot. Next step, we need to figure out P4. That's another straightforward calculation. It's the same as P3. We'll put that up at the top. Finally, the work in going from state 3 to state 4. That's the volume integral of P dV, now going from volume 3 to volume 4. Well, this one isn't 0. It is a horizontal line after all, and it's not right on 0. But we can pull out this P because it's constant. So remember, this is a constant pressure process. It's not a polytropic process anymore. That means that the pressure is constant and we can just pull that pressure out front. So the work in going from 3 to 4 is P3 times the integral of dV going from V3 to V4. That's a pretty easy integral to do. So we'll move that up and put in the values. Being careful with the sign here, we get that the work in going from state 3 to state 4 is minus 77.6 kilojoules. So now we have 3 values of work for 3 different processes. The total work associated with the sequence of processes is literally just the sum of the individual works that we computed. So 589 plus 0 minus 77.6 kilojoules gives us a total work of 511 kilojoules. This is a positive number, and you may remember that positive work tells us that energy was subtracted from the system. Again, we don't know what's going on with heat transfer, but from a work perspective, we know that energy was taken away from the system. If you look at our PV diagram, this should not be a surprising result. After all, state 1 started with a high pressure at some volume. By the time we got around to state 4, we had a much lower pressure with the same volume that we had in state 1. So somehow we got rid of all that pressure. Well, the way we did it was to do work in such a way that we subtracted energy from our system. That's how the pressure got lowered. One final detail worth noting, you may already have noticed that process 1 to 2 had a positive value of work and we were going to the right on the PV diagram. Process 3 to 4 had a negative value of work and we were going to the left on a PV diagram. That is a generalizable trend. A process that goes right on the diagram should have a positive work. A process that is vertical on a PV diagram should have no work, and a process that goes left should have negative work.